Going to listen to the second part of Tobias Fritz's lecture series, second and last part, which is duality theorems. And yeah, I'm just going to let you talk.
Yeah, thank you. Well, the plan for today is to discuss another duality theorem, Vergleichsstellensätze, that is still kind of more powerful in a sense than the one that I had presented yesterday, and also correspondingly a bit more subtle. And so it's going to also apply, give more fine-grained information in cases where yesterday's one does not apply. Okay, but just to finish up from yesterday, if you recall, I had given the representation theory example. So ordered semiring of representations of a Lie group, and I had mentioned that at least for a compact Lie group, my Vergleichsstellensatz applies to that, but I forgot to mention, or didn't have the time to mention, that that application is actually useful in the sense that we can actually classify the relevant homomorphisms and give a very explicit description of those. And this is something that I've done in the case of SUN. So for the representations of SUN, that means there now is a kind of essentially necessary and sufficient criteria that are completely explicit when one representation is asymptotically contained in another one. So this case is kind of solved in the sense that I suspect that the same, more or less the same techniques should apply to representations of a compact Lie group in general, but the technical details are still kind of subtle, and my representation theory knowledge isn't quite good enough to do the general case. So rep G for general G is open. Yeah, so in the sense of classifying the homomorphisms. Okay, but mainly today I want to talk about another totally different example, which I had already hinted at yesterday, namely the example of majorization between probability distributions. And so this is basically, yeah, a part of joint work with a bunch of people from Marco Tomamichel's group at CQT in Singapore. So this is Farouk, myself, Pasalo, and Tomamichel himself. But I'll just sort of, in this talk, limit myself to the simple case of majorization, where the results that I'm going to present on the asymptotics and catalytic majorization have already been known for something like 15 years almost. But we can do also things like matrix majorization, but that would be maybe a little too complicated to go into in detail. Okay, so this is going to be an ordered semiring that I'll just call or denote by major. And so its elements are vectors is what we would like to take. But in order to get a semiring, we should drop the normalization of probability. So that means we just have finite vectors or sequences of arbitrary non-negative numbers. And it's kind of convenient notationally to just consider these as infinite sequences, where just almost all terms are zero. And so this is an element of R plus infinity, where the infinity indicates kind of the topologist's infinity, maybe indicating that only finitely many terms are allowed to be non-zero. Yeah, then I actually want to also consider these modular permutations. So a semiring then this element is really an equivalence class of these, but just to keep the notation simple, I'm going to be sloppy and just identify P with its equivalence class. Okay, so now the pre-order is majorization, and I actually want to use a convention where I denote the majorization pre-order in the opposite way as it's usually done. That just turns out to be more convenient. So that means when we have the P and Q like that we define P to be less than or equal to Q if and only if there exists a bistochastic matrix T such that TP is equal to Q. So bistochastic meaning non-negative entries, and well, technically infinite, but of course should be only finitely many of its entries actually matter, since both P and Q are finite. And yeah, with rows and columns summing to 1, so that's bistochastic. And so intuitively, the way to think about this is that Q now somehow can be more random than P. So as we go up in the order, we increase the amount of randomness. There's a couple of equivalent characterizations of this condition, and maybe the most well-known one is the criterion in terms of partial sums of the decreasing rearrangements, also known as the kind of Lorentz curves. So this says that if we take the decreasing rearrangements, so which I denote by this down arrow, and form sums up to some m, then this should be greater than or equal to the corresponding thing for Q. So note here, this is the opposite than here, and I guess that's why one usually defines it the opposite way around, so that one matches this direction of inequality. And so obviously, I mean, this is not enough because here it's obvious that the normalization of P must be equal to the normalization of Q, otherwise there cannot exist such a T. So this is an additional condition that we'll need. So normalization meaning just one norm, where now sum over all the entries, that should be the same as that for Q. So these two conditions together are equivalent to
normalizing the V1.
No.
Okay. And also there's a characterization by like these what do you call them, like thief moves or whatever, where you
yeah.
Okay, just making sure.
Right. It's the same.
Yeah.
Robin Hood moves, I think.
Money press. So P1 arrow down is the biggest or the smallest?
We start with the biggest, and so intuitively, when we add a randomness like this, the biggest one can only go down. That's a sort of Robin Hood idea. If the richest person you can take and distribute to the others. Okay, and to indicate a bit of the significance of this, let me just illustrate the relation or state, recall the relation to entanglement theory via Nielsens theorem. So this is kind of a bracketed remark, Nielsens theorem, that when we look at pure bipartite entanglement, meaning that, let's say we look at pure states, so psi, and suppose when we take the Schmidt decomposition, so that means we write this psi as some positive coefficients, square root of pi, and then here we have some the first tensor factor analysis system, whatever states, doesn't really matter. We're orthonormal, I guess, and something else on both sides, and the square root here. It's obviously conventional, and that is useful in that now the PIs have the same normalization as the psi. Psi is a unit vector, then the P is a probability vector distribution. So, and so suppose we have another one with the corresponding coefficients Qi, then Nielsen's theorem says that we can turn psi using just LSCC operations into phi, if and only if, now here again need to be a little bit careful with direction of the order, if and only if now in my convention, if P is less than or equal to Q. So this would be the remark. And so, well, if we can do this, then roughly, or at least to understand the direction of the ordering here, the amount of randomness in the Schmidt coefficients can only decrease. And so this is how we get this direction. Wait, did I get this right? Yeah, right. So up in the order is more random. So that matches the intuition behind this. Okay. So just if you want to know why one might want to look at this majorization thing, an asymptotic majorization in particular, then just can keep this as motivation in mind. But it also comes up in other contexts like statistics, economics, matrix majorization in particular. Okay, so now what about the semiring structure? So far I only defined it as a set, as an ordered set. But the semiring structure is kind of the obvious one. I guess, I mean, the plus, we already saw this for the representation theory example as well. The plus is kind of direct sum in many cases. So by this, I just mean you kind of concatenate the two vectors, or you just, take both of them in sequence. Concatenate. And since we're doing it modular permutations, I mean, the order is arbitrary. And for the product, also, well, the obvious thing, tensor product, chronicle product, or just basically making the two distributions independent. That's the obvious thing. So maybe I can write this as pi qj as to indicate this is the sort of sequence, and again, I mean, arbitrary order. Yeah, so then major with these structures indeed becomes an ordered semiring, but now it does not satisfy yesterday's the conditions of yesterday's theorem, because now we do not have that the one, so the multiplicative unit, which is just the probability vector consisting of just a single one, is clearly not above 0, which is just the all zeros vector. Since they do not even have, obviously do not have the same normalization, only elements of the same normalization are comparable. Or it can be comparable. So that means yesterday's theorem does not apply, and we're going to need something else. But before I get to the statement of that more powerful Vergleichsstellensatz which does apply, let's just take a look at the homomorphisms in this case. And I like the semiring in particular because it's a really beautiful example of how one can classify the homomorphisms perfectly in at least some cases. And then how the semiring structure helps or comes in, enters in that classification. So what are monotone homomorphisms? As major to R plus. We could also do it for the tropical reals, but let's just take the usual reals for now. And the tropical reals, I mean, those are also going to be relevant, but then I'll just state the results for that later. Okay, so suppose we have such an F. No, let me try to be consistent and call it phi. So phi applied to an arbitrary P. So now suppose our P has non-zero entries P1 to Pn. Then the crucial observation is that we can write this P as a sum in the semiring of single entry vectors. So yeah, I want to just denote this now by this and just leave out the zeros, the trailing zeros. And now because phi is a homomorphism, obviously it's additive. Yeah, must be additive, and so I can just write it as a sum of the values of phi on these single entry vectors. So phi is uniquely determined what it does on these single entry vectors. And so what more can we say about what happens on single entry vectors? Well, that's where the multiplicativity is going to come in. On single entry vectors, let's say if the values are, when we're looking at a product, that when a single entry is a product R times S, well then this vector is just, again, product in the semiring of these two. And so here I can apply multiplicativity to write it like that. And now this is the multiplicative version of the Cauchy functional equation. So this is a very standard sort of thing. And that means that modulo some additional condition which follows from monotonicity of phi, that we can conclude that on single entry vectors, phi is given by just taking a power fixed. So there is a fixed exponent, let's call it alpha, such that phi on a single entry vector with value r is equal to r to the alpha, or some a priori alpha is an arbitrary real. But of course, the monotonicity constrains that to particular values. But so now that means in general, now we can use this equation, the additivity thing, to say that phi of p is equal to sum over I pi to the alpha. So modulo taking the logarithm and normalizing this, that means that phi is just given by Rayleigh entropy. Okay, so what's going on? Actually, yeah, just a maybe brief remark. That's what's going on here. A little bit more abstractly speaking, is that this matrix semiring is kind of like a group ring. On a group ring, the homomorphisms into some other ring correspond to kind of group homomorphisms. There's a kind of universal property making correspond to group homomorphisms. And major is basically a group semiring, and that's why we got this classification.
What is that? Sorry, I didn't catch it.
A group semiring.
Yeah, what's that? Like what group ring? What do you mean by group ring?
A group ring is just basically all formal linear combinations of group elements.
Yeah.
And then those form a ring with
Group
coefficients.
semiring in what sense?
And in the sense that this is actually isomorphic to the semiring that we get when you take natural numbers for your coefficients, and then use positive reals as a group under multiplication, because every p is in a unique way a sum of these single entry vectors, and these are positive reals.
Yeah.
And we multiply using exactly basically the multiplication that comes from here.
So,
And that's why the classification of the homomorphisms is so simple in this case.
Yeah.
Okay.
With this alpha plus alpha, that's due to Filipana, or
no, this is Cauchy.
no, but like this majorization setup with semiring structure.
Yeah, I don't know, to be honest. I imagine that is already in his paper, but that's more like my co-author's part.
We need to get r to the alpha as the unique as the only option.
Yes.
Yeah, it's a Cauchy theorem.
Oh, I understand that.
Yeah.
Like you want to get the idea of putting the whole thing in this
I've seen it in his papers. Yeah.
I mean, I wouldn't be surprised if it's, let's say, already older in some form. Okay. Yeah, please.
About the projection. So is the coefficient for specific, let's say, pi would be the number of times it's appearing in the
Yes, that's exactly it. Yeah. Yeah. Okay. Any more questions about the example of majorization for the moment with semiring? Then okay, I'll move on to now back to the abstract theory and to the general theorem. spent before stating that, I'm going to need like a few more definitions. And the first definition, or first part of this definition, is going to be a generalization or a more general version of the definition of power universal element I had given yesterday. So the definition I had written down yesterday was actually specific or intended to apply in the case where this inequality holds. But in general, the definition that I think somehow the correct one is this one. So we have an element that's greater or equal to 1 in our order semiring. Then this is power universal if for all A, B, and S. Well, the condition that I had written down yesterday was there exists a K in N, basically such that any element is already upper bounded by some power of U, right? But now we clearly cannot postulate this since if we look here, for example, only elements of the same normalization are comparable to begin with. So a nice way to address that is to say that if we have two elements that already are satisfy an order relation, then we can also find a bound that goes the other way around if we use sort of padding by a suitable power of U. So then exists a K such that now B is upper bounded by U to the K times A. This is a definition that turns out to work well. Okay, well, let me get to the example after finishing the other parts of the definition. So yeah, to be able to state a theorem and just need some kind of two minor.
But then if 0 is bigger than 1, sorry, if 0 is smaller than 1, which you don't need, but could happen, then there is a case such that 1 is smaller than u to the k times 0.
Sorry, yeah, I forgot to say non-zero.
Right.
Yeah, thanks. Basically, many of these things, I mean, many of the statements one ends up making in this theory are kind of for all non-zero semiring elements. It's as if one just should omit the 0 from a semiring to start with. I'm not sure. Yeah. Okay, so now there are two more technical conditions, which are actually in yesterday's setup are actually automatic. But now under the weaker assumption we do not have this, I need to postulate them separately. And so one is that S is 0 sum free. And so now that is another way to kind of exclude the ring situation, that if we have two elements that add up to 0, well, the only way that this can happen is that if they're both already 0. Or well, obviously, if just one of them is 0, then the other one is necessarily 2. And similarly for the multiplication, that there should be no 0 divisors. So S is a semi-domain. This actually, yeah, a more or less standard term in semiring theory. If we have no 0 divisors, so if AB is 0, that can only be the case if one of the factors was already 0. Okay, so now example, our majorization semiring is a 0 sum free semi-domain. It's not so difficult to see, basically just because we have the normalization homomorphism. Just look at the normalizations of A and B. If this equation holds, then clearly both A and B must have 0 total probability, and so they're both themselves 0, and similarly here. And what about power universal elements in this sense? So that's not so obvious, but it's still not difficult to show that actually every probability vector except for the trivial one, so every probability vector is actually not a delta or not has some randomness, is the power universal element. You can take the feather coin. I guess that's an obvious canonical choice, but for the theorem itself, for the application, it's going to be relevant that every u greater one is power universal in this case.
So anything with support at least 2.
Yeah.
Yeah.
And is normalized. And so that's what's contained in this inequality. So the inequality means, first of all, u must be normalized.
How does this inequality says it's normalized? U?
It says in particular that it's normalized.
Yeah.
And that it can't be the delta.
Yeah.
So it has support at least 2.
Yeah.
That's sort of encoded in this inequality. Every such thing is power universal. And it's kind of simple arguments and involving, look at min entropy, for example. Okay. Now I could state a theorem, but before doing that, I actually want to present one more example of an ordered semiring that will be useful to understand the theorem when it comes. So another example of an ordered semiring, and this one is kind of not directly motivated by any application, but more like just to illustrate the theory itself and to see what sort of things happen typically in ordered semirings where 1 is not greater or equal to 0. So namely, let's take look at just polynomials of degree 1 with non-negative coefficients. Or in other words, let's just take a polynomial semiring with non-negative coefficients in one variable and just say that declare x squared to be 0. So that means this we can identify the elements of the semiring with just linear polynomials with a, b, and r plus. And well, where addition, of course, is just coefficient-wise, and multiplication is given by multiplying them as polynomials and neglecting the x squared term. Right, so that means we got a b squared plus b prime plus a prime b times x. And so far, this is nothing all that special, I guess. I mean, sort of familiar kind of construction if you've studied some kind of algebra. But now let's make this into a pre-ordered semiring. And basically what I want to say is that in some sense the A plays the role of the normalization. And the X is still somehow a quantity that does not affect the normalization, but is somehow infinitesimally positive. And based on this intuition, we can introduce a pre-order, or well, an order. Let's say ordered such that a plus bx, so this is equal to a prime plus b prime x, by definition, if and only if a is equal to a prime, and b is less than or equal to b. So this is a kind of paradigmatic example of the sort of thing that one needs to deal with. And here, and all this example is supposed to illustrate that it's not enough to look at homomorphisms anymore. Because if we just take now look at homomorphisms, the only homomorphism that goes back to R plus is just the one that evaluates at 0, or the one that takes a plus bx to a. So 2 R plus is this one. So this cannot distinguish somehow elements that are pre-ordered relative to another at all. And we cannot hope to detect the asymptotic preorder using only
Is
homomorphisms.
this semi-domain? This is what is this a semi-domain?
Um,
X times X is 0.
Yeah, that's a good point. Actually, it's not, and that's because I've somehow simplified it a little bit for the purposes of the presentation.
Yeah.
But what I actually want to take is a strictly positive.
Yeah.
And then put the 0 back.
Thanks. I'm gonna
Yeah,
annoy you with
that's a good point.
Yeah. I'll keep annoying you with these questions. So it's being zero.
No, that's good. I mean, I should be precise. Well, okay, even if it's not a semi, yeah, well, like this, it's what I actually want. And then we can take even the b, can allow it to be negative. That's not an issue. But yeah. Okay, so and the homomorphisms to R plus at least don't tell us much. And the tropical reals, and that's even worse. It's not so hard to see there isn't any homomorphism to the tropical reals at all. And there is none. So that means in order to say anything about the asymptotic order, in order to have any hope of getting a duality theorem, we need to be looking at more things than just these homomorphisms. Okay, and so, well, basically what I would want to do is to have a kind of map that maps A plus Bx to B. That's clearly not a homomorphism, but it is something else, another kind of map that's frequently appears in an algebra context, namely a derivation. And so definition, I want to be looking now at derivations at particular homomorphisms. And so yeah, before I'll write down what a derivation is, let's just say a homomorphism phi from S pre-order semiring to R plus. Let's call it degenerate. If well, it's not actually monotone, but if it's monotone in a trivial sense, that on any order pair, phi takes the same value. So, for example, this thing here, right? We evaluated a same value. In the majorization case, it's the one norm or the normalization. It's an additive, multiplicative map that takes the same value on every order pair. Okay, and so now the point is going to be that we also need to look at the derivations at degenerate homomorphisms. And so now what do I mean by that? Derivation, phi derivation given well, any homomorphism phi is a map D from our semiring to R. So now here we can also take negative values. That is additive and satisfies a version of the Leibniz rule. So the product rule for differentiating functions, namely, when I apply D to a product of elements, then I sort of should be getting A times D of B plus D of B, D of A times B. But that doesn't quite make sense because A and B are semiring elements, while here we're at a level of numbers. So this is just supposed to be phi instead. And then, yeah, a phi derivation is a map like that. Okay, I guess I should wipe again. So just to see how this solves this problem, let's briefly look at that again. So on this would be in a first example on R plus. Yeah, on that thing up there, we have that this just mapping to A or evaluating at x equals 0, A plus Bx mapping to A is a degenerate homomorphism. And now projecting to the B, A plus bx mapping to B is a phi derivation. Well, and this is something that the Leibniz rule is actually precisely this kind of formula for the product, right? Or for the linear term in the product. Here we have phi of the first factor, d of the second, and the other way around. So this would be the first example. On our majorization semiring, we have also derivations or a derivation that needs to be considered. And this is maybe quite surprising what it is. But let's see first of all what the degenerate homomorphisms are. So on major, just taking, I already said this, taking the one norm or the normalization. This is the degenerate homomorphism. And we've classified all the monotone derivations at this degenerate homomorphism. It turns out that they're all scalar multiples of a very well-known quantity, namely Shannon entropy. So derivation or normal at the normalization homomorphism, pi log pi, and its scalar multiples. Well, these are all. So of course, I mean, scalar multiple of the derivation is again the derivation. Sorry, I should say monotone. And then you have positive scalar multiples. And to see the Leibniz rule, I think this is quite instructive. I will briefly go through this. And so I'm using this definition also when P is not normalized. There's maybe some kind of ambiguity of how would we define Shannon entropy in the unnormalized case. We could do other kinds of things, but this is just the literal expression that we can use, and that turns out to work. So let's check just the Leibniz rule. So what is the Shannon entropy when we have a product distribution? Well, obviously then it's just we sum over both, and we have the products in here and the log of the product. But now obviously this turns into a sum of logarithms, and so we can split this into two separate sums, pi qj log of pi, and then a second term that contains log of qj. So now what do we have when we look at this term? The qj, we can just, split this into two separate sums again, right? These are independent. And here we just have the one norm of q and the entropy of p, and the other way around for the other term. So that means this is one norm of q, h of p, plus one norm of p, h of q.
H is d, yeah? I guess. You want to write d for h, yes.
Right, yeah, thanks. No relation to relative entropy in this case. Okay, and so to prove that this is actually these are the only ones, scalar multiples of this, that's basically standard characterizations of Shannon entropy. Can derive the chain rule from the Leibniz rule and this sort of thing. Okay, so now finally got to statement of the theorem. So here we have, zero sum free order semi-domain. These assumptions are all quite technical, and I'll actually formulate a bit of a simplified version of the result. Just let's say one that is doesn't apply quite as generally as the most general one, but still applies to the majorization case. So what I'm writing down here is a little bit more restricted. So such that the observation that I had mentioned for the majorization case earlier, that every element that is strictly above 1 is actually a power universal. So let's assume this this can be relaxed, but just for simplicity. And also, I want to assume that we're given a degenerate homomorphism that behaves like the normalization does in the majorization case. So with degenerate homomorphism, and I just also want to denote it by a norm symbol. And I also want to assume, in addition, that the preorder is not too small. And what I mean by that is that whenever we have two elements with the same normalization, then they should be somehow indirectly comparable. So then I want that they have a common upper bound. So this is, in a sense, a partial converse to the degeneracy. I mean, if we have this, then certainly A, B, and C all must have the same norm, because this norm homomorphism is assumed degenerate. But also, then when you assume this converse, and this somehow encodes that the preorder cannot be too small. Okay, and so now what is the actual statement? So now let's say we look at two elements, saying elements that are both above one. So in the majorization case, meaning they're both probability distributions support at least two. And obviously, we want to decide the asymptotic ordering. And so that means going to be considering two conditions. The first one is, again, the sort of comparison when applying any homomorphism, and now also monotone homomorphism, and now also derivation. So this first condition, now sort of the spectrum, geometric inequality on the spectrum, that phi of x is strictly less than phi of y for all monotone homomorphisms by going from S to K. We're now by K. So in yesterday's theorem, if you recall, the homomorphisms were valued in the non-negative reals and in the tropical reals. But now in this case, that's actually not quite enough. And I also need to consider homomorphisms that take values in the opposite of the non-negative reals and opposite of the tropical reals. So that means these would be monotone with values in R plus with the opposite preorder, or equivalently, I mean, order reversing with values in R plus. And likewise for the tropical case. One indication of why you can maybe see that one would expect something like this is that now when we do not have that one is greater or equal to 0, we have more symmetry. We can basically take the order reverse of the preordered semiring, and it's still one modulo the power universal thing here, but one can relax now. Okay, so yeah, one needs to consider 4 basically regimes. And these kinds of regimes also correspond to, maybe you've seen for the Rani entropies, considers various parameter regimes. It's pretty much the same distinction here. So this is for the homomorphisms, and then we also need to look at the derivations. So this is d of x less than d of y for all monotone derivations at our degenerate homomorphism. Monotone derivations. Okay, so this is the geometric part. The algebraic part, obviously, the thing that we're actually interested in, the asymptotic preorder. That's going to be condition 2. And this is kind of very similar to yesterday. And I could actually use the exact same formulations as yesterday. But let me simplify it a little bit. Because of the assumptions that I have now, I can formulate it in a bit of a simpler way. Then let's just say that the asymptotic ordering really holds on the nose. So this is, and I'll just say how conditions or properties 1 and 2 are actually related, but for now, let me just finish writing them down. And there is non-zero C such that Cx, so we also have catalytic ordering, and this is again basically the same as yesterday, and we can take C, we have even a specific form for the catalyst, name this thing that is a little bit like a finite geometric series. Okay, so consider these two conditions. And now the statement of the theorem is that 1 implies 2, as you may have expected. That's the difficult part, that we can conclude asymptotic ordering from those inequalities. And the easy converse is just that if any of these sorts of things holds, so any of these inequalities holds, I mean, this one obviously for n at least 1, and if any inequality S in 2 holds, then we kind of, for more or less trivial reasons, we get the inequalities in 1, but in the non-strict version, of course. Then 1 follows non-strict inequalities. Okay, yeah, I guess I'm out of time. If you want to see it, I mean, I could still spend a few more minutes on the majorization case and see how that works out. That one gets the Rayleigh entropies very explicitly, including the normalization factor, and just see what this amounts to in that case. But otherwise, yeah, I'll stop for now.
I mean, that's interesting. We can take it off. We can take it offline, like later. We can, but it's interesting to talk about it. Actually. Yeah. Huh?
You can also continue on the board and break.
Yeah. Yeah. So for now,
Sure.
Thanks a lot. And are there questions? Yeah.
I have a question. So it's a very long time ago, but I looked at kind of like where the proof of like Strassen's theorem and so on come from, and they seem to be kind of like taking this semiring, I think, and then they're looking at ideals of this, and then to every ideal there's like this, there is this homomorphism. Right? It's something like that. I'm kind of wondering, you didn't mention that now, but I'm kind of wondering these generalizations that you're discussing, like what is sort of what is different, or
yeah. Thanks for asking. I didn't. Yeah. I really would have liked to. I mean, to say more about the proofs, but I mean, thought it was better to focus on the statements and try to explain those well. But so as far as I remember, Strassen's proof was a reduction just to standard theorem for ordered rings, right? A Caddis de Bois Positivstellensatz, which is in some sense a version of Galfand duality again. But these theorems, I mean, are proven really completely from scratch. And the reason, or one way to see that this is kind of necessary, is that they involve the homomorphisms to the tropical reals. And these you cannot embed in any ring. So you cannot apply just techniques or results from ordered rings. You cannot expect to do that.
Like one way to think of Strassen's proof is if you roll it out, if you expand also the Caddis de Bois proof and like make it one big proof.
Yeah.
Then what happens is you have the Strassen pre-order, like a pre-order, like it needs certain properties. You look at all the extensions of it, extensions of this pre-order, and you look at the maximal ones, which exist, and then those maximum ones are the homomorphisms, the monotone homomorphisms. Okay. That's kind of the high level of how that goes.
So
here I don't know
exactly, that's also like from your thesis, and so yeah, and in terms of the high level structure of the proof, it's the same. Just basically use Strong's lemma to show there's a maximal extension of the preorder that distinguishes two elements. And then the main difficulty is to show that such a maximal, so actually we do this in a semi-field case where the non-zero elements are available. And then show this, the most difficult part is to show that this, such a maximal extension is the total preorder.
Yeah.
That would be, and then basically show that this sort of thing, then one has enough separation by mapping to R plus and TR plus. That would basically be yesterday's thing. And for today's thing, it's kind of similar, but more subtle, and really the difficulty is a lot in technical details. But conceptually, the proof isn't so original.
And to follow up question, I mean, this may be just playing my ignorance, but is this now like a generalization of like the Strassen theorem, or is there something that I'm overlooking? No.
In this version, it's not, but yesterday's one is.
What is in this version? Like I don't know, zero sum free order semi-domain.
Yeah. So that we have this one, that we have basically this degenerate homomorphism.
You have it, check.
Yeah.
Okay, and of course there's situations where you don't have.
Yeah.
Okay, and once you have that, if you have that, then
Like in Strassen situation, you never
Yeah,
I guess, because of the normalization.
And because the natural, we have one greater equal to zero.
yeah.
Whenever we have one greater equal, that already precludes
Makes things grow always. So you cannot have a constant.
but I do have a formulation that actually comprises both. It's just, I mean, I didn't want to make it too complicated. I can also, yeah, basically have any number of such degenerate homomorphisms, and so then when that number is zero, it recovers. So yeah.
What's also, yeah. So I think I have to ask this. That we can also do. Are there more questions? I'm thinking about your second statement. Is Strassen's version also what you talked about yesterday? There's a statement where you have also a little bit of overhead, like y to the n plus little of n.
Sure,
y
yeah.
to the n times.
If include then an overhead here, there's, let's say, a fixed power universal element u, and then or even just an n plus sublinear power of y.
Yeah.
Then I mean it becomes equivalent to one of non-strict inequality.
With the non-strict, yes.
Yeah. But that's kind of a simple corollary of this, and like these sorts of statements are a little tighter.
That's a corollary, you say.
Yeah. Because just when you add some additional kind of small padding of photocopies of y, then, and if you just have non-strict inequality, basically you replace this y by y to the 1 plus epsilon, then I mean you got strict inequality. And then you can apply this and derive.
Just by replacing y by y times 1 plus epsilon.
Yeah, I mean morally speaking, which,
Yeah. Okay, good. Yeah, that's fine.
And I think this sort of reason is also why, if you look at the Positivstellensatze in real algebra, why they're typically formulated with strict inequality and only one implication.
Yeah.
Because then you get a version of non-strict inequality and an equivalence as the kind of corollary of that. But a strict inequality version is typically considered better. Right. I mean, in the end, it's not that much stronger because actually I first derived the equivalence version of non-strict inequality and this from that, but
So it's kind of a good.